Okay, so questions from last class. Do we have any questions from last class?
I have a bit of a question about why why we are representing the operator in terms of projection operator.
Right.
What's the purpose of that?
Okay, why do we have the operator in terms of the projection operator? Yes, that's a very good question. And this is because it's a very good question. So there's a very nice geometrical reason for that. So for example, so I'm going to discuss this in terms of an analogy from undergraduate physics. So in undergraduate, well, you are undergraduates, I guess. So for example, suppose you take a velocity vector. Okay, so you have a particle, and suppose it has some velocity in this direction, right? Right. So this is a physical quantity, right? The velocity of a particle. Now suppose that one of you, say Shujosh, is measuring this system, and this is Shujosh's reference frame. Okay.
Mm-hmm.
So let's call this S. So in this reference frame, say V has a particular value, say just 0.5, say I plus say 0.6 or say 0.4 J. Okay.
Mm-hmm.
Now, suppose that Moon is measuring the same system but from a different reference frame. So this is say suppose this is Moon's reference frame. Okay. So this is for Moon. She's measuring the same vector, but for her, sorry. Let me just make the numbers a bit easier to work with because, yeah, let's just be 1 on 1, okay? So that means that this is square root of 2, right? The length of the vector. Do you agree?
Yes, sir.
So yeah. So but no, in Moon's reference frame, there is no y component. So what Moon is measuring is this, right? So this is, I should have color coded things, but so this is the reference frame, the basis for Shujosh's vector, and this is the basis for Moon's reference frame. Okay. Now, you know that this vector and this vector are the same, right? They're representing the same physical quantity. Do you agree?
Yes, sir.
Yeah. But their representation in different reference frames or different coordinate system is the components are different because you're choosing different bases, right? For the same vector space. So what the projection operator does is that it takes a vector, say in quantum mechanics, psi, and suppose that you have some basis, say psi, let's not call it psi, let's call it, say, phi I, okay, where I goes from 1 to n. And you have another basis which is called, say, chi I, where I goes from 1 to n. Now these are bases on Hilbert space, okay?
Mm-hmm.
So let's say this could be, say, Shujosh's basis, and this could be Moon's basis, right? Now, what happens is that we saw that the identity operator can be expressed in terms of the sum of all the projectors. So in Shujosh's basis, this is going to be the sum of all the projectors, right?
Mhm.
But in Moon's basis, it's going to look different. It's going to look like that. Okay? Now, this is the identity operator, so we can insert the identity operator here. This is, psi multiplied by the identity is going to give me psi, right?
Mhm.
Now, I have a choice in expanding this in different bases. So if I'm expanding it in Shujosh's basis, then I get phi I, and there's these numbers, phi I, psi. Now these are the basis vectors, right? And these are the coefficients, like the coefficient here and the coefficient here. So these coefficients are telling you what the component of this vector what the components of this vector are along the different basis elements of Shujosh's basis. But if I wanted, I could have done a different calculation, expansion, where instead of Shujosh's basis, I could have used Moon's basis. And then these complex numbers would give me the components of this vector along the different directions in Moon spaces. So you see, now that why this is so useful is that the projection, the expansion of the of an operator in terms of projection operator give us very easily what the component of a state is in that direction. Now let's look at, say, an operator which is not the identity operator, say lam A. So A has some eigenvalues, let's call them, say, AM. So A acting on, say, some eigenvector, so its own eigenvector, psi m gives you, say, small am of psi m. Okay?
Mhm.
So we can write A as sum over 1 to m, A of m, and then psi m of psi m. Okay?
Mhm.
Now, what this is saying is that it is saying that A has an eigenbasis given by these vectors psi of m. And in some sense, when you're asking questions about A, this is the preferred eigenbasis. Because in that eigenbasis, A is diagonal, right? Remember I said that, this is essentially saying that we are writing A as a diagonal matrix in some basis.
Mhm.
So that's what you're doing. So now, suppose I give you a state, say some physical state, say chi, and then you want to, compute what the expectation value or the average value of A is in chi. So if you just now compute it, what becomes is that if you just like use this expression, so this is what? Bra of chi, A ket of chi. And then what you can do is that you can introduce the identity twice. Once here, and once here. So this should be, sorry, M. So M and N. Are you clear what I'm doing here? I'm
I'm not
inserting the
too
identity twice
sure.
here.
Oh yeah, I see. I
But
see.
the identity is here and the identity is here. And I'm using this twice. Not this, I'm using this thing twice. Okay?
Oh, okay.
So having used this, now A is acting instead of, the thing is that we know how A acts on its eigenbasis, but we don't really know how A acts on chi. So this is basically a shortcut to figure that out. So A acting on psi n gives me A n, and then I have psi m psi n. And here I have psi n chi. What is this? This is the projection of chi along the nth direction of the psi basis. Similarly, this is the complex conjugate of that. But because of A's action on this, I now have a number. So this number, I can put it, say, here, because it's not an operator anymore. And this is an orthonormal basis, which means that this is equal to delta mn. So I basically have m comma n, A of n, then I have chi psi of m, and then delta mn psi n chi. Just bear with me. Now, here there are two sums. We can do one of these sums, say the sum over m, using the Kronecker delta. We know that the property of Kronecker delta is that it is 0 when m is not equals to n. And when m equals to n, it is 1. So this sum over m, only the m equals to n term is going to survive. So therefore, the result of this would be A of n chi psi of n. Because of the Kronecker delta, this m becomes n. And this was already n, so this is it. Now what is this? This is the complex conjugate of this. So then basically I have n an chi psi of n squared. So the average of A is this. Now we know from the definition of an average is the average of a quantity is its random. If it's a random variable, its values, say an, and the probability that value is going to occur. So that means that this thing is equal to the probability that if you make a measurement, you're going to get the value an. Okay, so you see that having this projection operator, so this is P probability, not projection. Okay, but we have used the projection operator extensively in coming up with this very beautiful physical expression for the expectation value of A.
Oh, I see. Yeah.
Okay, so yeah, this is a very, very good question, and okay, so any more questions?
No, I don't have any questions at the moment.
Anyone else? All right, so let's carry on then. Did anyone have any questions regarding this explanation? I mean, this was pretty involved, if you like.
I'll have to go through this a bit more to
Yeah,
really
this is
understand what's
non-trivial.
going on. Yeah.
This is very non-trivial, and I will give you examples to work through. You have to come to the tutorial. This is not an easy class, okay? This is not going to be an easy class. All right, so let me review, or let me pick up where we left off last time. Last time, we said that if I have a Hermitian operator, say A, I can do a decomposition of this operator in terms of its projection operator, and it's going to be weighted by the eigenvalues. So I used lambda last time, but let's use small a. And because we are assigning eigenvalues in relationship to eigenvectors, it is a good idea to even label the eigenvector by the eigenvalue. Okay, this is something that we will do a lot. That if A is acting on some eigenvector and its eigenvalue is small a, its eigenvalue is small a, then what we do is that we even label that eigenvector by the eigenvalue. Okay, so this is a very, very useful way of labeling eigenvector. So this is what this is, and in terms of physical interpretation, well, what we said is that this is equal to AI, the projection operator Pi. Okay, and this is known as the spectral decomposition theorem. Okay, so this is, in matrix language, what we are saying is that if we have a Hermitian matrix, then there is a basis in which the Hermitian matrix can be written in a way that it is diagonal and the diagonal elements are real numbers. That is all that we are saying. Okay? But we are saying it is in an unfamiliar language.